This is the second part of conditional distributions, and in this video we are going to be considering the conditional distribution of jointly distributed continuous random variables. Let's imagine that x and y are jointly distributed continuous random variables with joint density function f of xy. So now the conditional distribution for x, given that y equals y, has density, and the notation is analogous. F sub x given y equals y of little x given y equals y is, and this is an analogous definition except we're using the densities, not the mass functions, is f of xy, the density function, divided by the marginal f sub y of y, and over the appropriate support, So the analogous definition, of course, holds for y, given that x equals x. The density f sub y given x equals x of y given x equals x is the joint density divided by the marginal of x over the appropriate support. That I keep saying it, it's important, we're going to see in just a moment. So let's look through at a continuous example. So let's let x and y be jointly distributed continuous random variables with density given here over this support. So 2/3 xy over the support given there. So that support turns out to be exactly this region here, from x is equal to 0 to 2, and y is from 1/2 x to x. So it is that triangle there. Now, I want us to find the marginal distributions. I want us to find a whole litany of things. I want us to find the marginals. I want us to find a continuous distribution density function. I want us to use that to find probabilities. I want us to find a CDF. I want us to find the conditional distributions, and you'll notice what's the difference between these two here. Well, one, I've actually put in a value, x equals 1. The other, I'm just saying for any general x, for x equals little x, and the other way around for the other conditional, right, for x given y equals y, and then an expected value. So we're going to do all of that for the continuous case. So let's start with the marginals. If we want the marginals, f sub x, well, we are integrating out the y. And so that means we are integrating for any y value, right? We're using this. For any y value, we're integrating from 1/2 x to x of the density. We're integrating out the y, and you end up by getting here for the marginal. Now, we're going to be a little bit more precise. We're going to be very careful to add the complete density function, because when we're going to see in the next marginal, that's going to not be quite so obvious. So here, this leaves, right, 1/4 x cubed, for what's left over is over here from 0 is to x to 2, and 0 otherwise. Now, the density for y, the marginal density for y is a little bit more complicated, and it's a little bit more complicated because of two possibilities here, right? If we rewrite our region as a type 2 region, well, then we have to split our region here, because the boundary on the right and the left are not the same. If we go here, right, then the boundaries are from x is y to x is 2y. But if we're up here, then the boundary is from y to, not to 1, to 2, that's a 2 there, to 2, to x equals, that's 2. There you go. So we have to be careful because those require different integrals because they are different boundaries. So we're going to do each of those integrals. The first one from y to 2y. So if we're integrating out the x, we're integrating out the x from y to 2y of the density, we get y cubed. But that is only valid, here from 0 to 1. So y cubed from 0 to 1. On the next region, right? The next region, which was from y to 2, integrate out the x of the density, and you end up by getting this. So you notice that's a different formula. Well, that's okay because it applies for different y values. From y is 1 to 2, we use this formula here, and then we've got 0 otherwise, right? So we have different intervals for y that we have to be a little bit careful about here for the marginal density, density function for these guys. That was the first one. Now the second we're asked to find here, the second part B, we're asked to find the conditional distribution. We're asked to find the density of y given x equals 1. So if we apply the definition of I want to say continuous, conditional density f sub y given x equals x of little y given x equals x. This is the definition, right? It's the density divided by the marginal. That is the definition of a conditional distribution. Now, we don't have just every x value. We can put in x equals 1. And so if we do that and put in x equals 1 everywhere, for x we put in 1. For x we put in 1, which means that we can apply this rule using those values, right? So our f sub x y was 2x, 2/3 xy, f of xy, I think I might have said sub there, the joint density, plugging in x equals 1, and you get this value, right? The marginal for x was 1/4 x cubed, so over 1/4 x cubed. And this is actually pretty easy to simplify, but some of them aren't. And so in fact, plugging in a value always makes for a simpler expression, right? And so you can simplify this and get 8/3 y for x equals 1. Now we're going to see in a later question a more general one for any little x value, which would end up by giving us this first if we did calculate it for a general x value to begin with. But given that we're asked this, no pun intended given there, because we're asked for a specific value when x equals 1, we might as well plug it in. Now, let's take a second here and think about what this is giving us. Here is the support again. Here is the support that we had before. We're restricting ourselves to x equals 1. So x equals 1 is here. Incidentally, when x is equal to 1, the y values vary between 1/2 and 1. So when I kept saying above, over the appropriate support, this 8/3 y as a final answer is wrong, because it is 8/3 y for y between 1/2 and 1, because that's what happens to the y values when we restrict x equal to 1 and 0 otherwise. So this is the complete answer. Without the appropriate support, your density function is practically meaningless. So what is actually happening here? Well, in the discrete case, what were we doing when we took the conditional? We were restricting ourselves to a single column. And figuring out the distribution along that column. The analogous thing is happening here. We're restricting ourselves to a single x value. But if we look up here at my 3D representation here, if we restrict ourselves to a single x value, right here, then our density, actually this is not the correct graph of the density function, it's drawn so that it's easier to imagine what's happening. Let's imagine this was our density, is a surface. It's a surface, and the probability we know is a volume under that surface. But if we restrict ourselves to a single value of x, well, what happens? Then we get an area underneath. And if we remember from our univariate, our single variable probability, well, an area under a curve for single variable is probability. And so that's exactly what's happening here. This restriction to a single x value has given us y values that form an area, a probability curve, and that is the density function that we have just found here in a single variable case, right? It's under a surface, but it is one dimensional, well, one variable, right? It's area. So that is what the density is, and now that we have that density function, we can use it to calculate probabilities just like you would as if you'd been given this from the start, right? You have a joint probability that you calculated a conditional density function from, right? But last course in probability, you might have been given this density function and just asked to use it. Well, now that you have it, you use it exactly the same way. So the probability that 1/2 is less than y is less than 3/4 given x equals 1, well, now that you have the density given x equals 1, you don't really need to do anything more with this. You just use your density function. And to calculate probability in a single variable case, well, you integrate your density and you would get this as an answer. Now this is a little, well, it's not tricky, it's easy, but it's a little subtle. What is the probability that y is greater than 1 given x equals 1? Well, take a look at your support here. It only goes to 1. If you're greater than 1, what's the density? It's 0. There is no probability out there, so the answer is 0. So that is to underscore that this appropriate support is crucial. I mean, you can also see it on the graph here, right? Y doesn't go above. When x is 1, y does not go above 1. So in this restricted case, the probability is 0. That support here, getting that right, is crucial. We can also do the CDF, right? The CDF. Why not? Now that we have this single variable density, anything you did with a single variable density function can be done again. So if you want to find the density, it is, well, it's this integral, right? It's this integral keeping carefully in mind, speaking is hard sometimes, keeping carefully in mind that when you're below 1/2, when you're outside there, your cumulative density is 0, and when you're above 1, when you're outside, you've accumulated probability of 1, and then in between, you've got your antiderivative. So once you have that density, you use it exactly the way you would use any density. So we have done A, B, C, D, and E here. These are asking us to find a conditional distribution not for specific values, but for any x, and the analogous one for any y. So we're going to go and apply the same formula, but we're not going to plug in values for x and y. And then we are going to use our answer here, plug in a value of y is equal to 3/2, and then use that for expectation. So let's do f and g, and that will be the end of this example. Now, here, what do we have? We have the conditional distribution. I have to concentrate so hard not to say continuous. Conditional distribution, f, the density f sub y, given that x equals x for some unspecified x value. But that is just a constant. X is going to be just a constant. Y is our variable, right? Y is our variable. Our final answer will have x's and y's in it, but x will be a restricted constant value and y will be allowed to vary. That's what's going on here. So if we do that and plug in the density the joint density and the marginal in their full values without plugging in any value for the x, we can simplify and get this, but of course on the appropriate support. And so for a restricted x value, y goes from 1/2 x to x, so with the correct support given and 0 otherwise. Flip it around. Well, flip it around. We had that difficult density, that difficult marginal density when we first did this. We had to split that up into 2 regions, right? We had to split it up right here, and so we have to do the same thing when y is between 0 and 1. So we're applying the definition, the joint density divided by the marginal density. When y is between 0 and 1, our marginal density was y cubed. When y was between 1 and 2, our marginal density was this function. The joint density is still the same on both. So you have 2 different expressions depending on where y runs and 0 otherwise. Simplified expressions, there they are. And again, with that support correctly identified, right? When y is between 0 and 1, x is between y and 2y. When y is in 1 to 2, x is from y to 2. So now that we have those, if we did want to use one, right, we could plug in y is 3/2. Y is 3/2. Plug that in. Well, 3/2 is in this interval. So I could use this function and get the appropriate conditional distribution. Get the appropriate conditional distribution of x given that y is 3/2. So plug that in, and here we get that distribution which simplifies to this, and with the support adjusted. Y is 3/2, so this is from y to 2, so from 3/2 to 2. Now that I have that value, all I do, if I want the expected value of x given y is 3/2, well, that given y is 3/2 has been taken care of already. I just do the expected value. I do what I would do for any single variable distribution. So I integrate over the entire support of x times the density function, and I get my expected value. One last thing to tell you. What about independence? Independence and conditional distributions, conditional probabilities are intrinsically related, right? And events A and B are independent if and only if the probability of A given B is just the probability of A, right? As if it doesn't matter whether B happened. Joint random variables were independent if their joint density was the product of their marginal densities. Let's take a look at what happens when we talk about the conditional distribution and apply independence of the joint variables. Something lovely, it's going to match what happens for conditional distributions of events. So if we have the conditional distribution, the density f sub x given y is equal to y, of little x given y is equal to y, that is a mouthful of the density here. Here's the joint density divided by the marginal density. If x and y are independent, then the joint density is the product of the marginal densities. And guess what happens? The marginal density of y cancels out. And so I have the marginal of x, right? As if the given y equals y didn't matter. The same idea that you had for independence of events. Analogously, if you look the other way around, right? The same thing here, you are taking the density, the joint density dividing by the marginal density. This time the marginal of x cancels out, and this, you get the marginal of y. So the probability, the density of f sub y given x equals x, of y given x equals x, it's like this part didn't matter if they're independent, right? That is a lovely result. It matches exactly the independence of events, which means that conditional distributions in the independent sense are the marginal distributions, which means that the probabilities that you'd calculate given that y is equal to y, if x is independent from y, that's just the probabilities that you would calculate for x. The same thing for the expected value, right? If these are independent, you don't need to take into account that y is equal to little y. So let's look at one last example here. Suppose that we have x and y that have joint density 1/6 over this rectangle. Calculate the expected value of y given that x equals 2. So I haven't mentioned independence because we should be able to notice it. Since the support is a rectangle, we had a theorem, and the density is a product of two functions, right? They are constant functions, but they can still be written as two functions of x and y. A theorem told us that x and y are independent. Therefore, the conditional expected value is just the expected value of y. So what I need to know is, well, what is the expected value of y? What is the distribution? Since f of xy is a constant, x and y must be uniform. X is on 1 to 3, so x is uniform 1, 3, which gives me the density b minus a of 1/2. Y is uniform 0, 3, right? Y is on 0, 3, so y is 1/3 its density function. So the expected value of a uniform b minus a over 2, 3 minus 0 over 2, 1.5, no integration needed. Now, what if we hadn't noticed? What if we hadn't noticed? Well, let's just calculate this as if we hadn't noticed. And so what we would need is the marginal density, right? We would need to calculate this conditional density to find the expected value of y given x equals 2. We need to calculate, we need to have the joint density, we need to divide by the marginal. So we calculate the marginal, we'd integrate out the x and we would get 1/2. No, we would integrate out the y and get 1/2 for 1 to 3. We would then take the joint density and divide it by the marginal density. 1/6 divided by 1/2 gives me 1/3, which incidentally I knew, but if we hadn't noticed that, we'd have the conditional distribution here from 0 to y to 3 is 1/3. The expected value of y given x equals 2 is the expected value of y. We wouldn't have known that if we didn't notice. We would integrate, there's a y missing, y times 1/3. Somehow y appeared in the antiderivative though, and we would get this value x, y, expected value of y given x equals 2 is 1/5, which was the value that we had above by noticing that these were independent.